Hello everybody, and welcome to the beginning of section 5.2 on diagonalizability. This is page 100 in the workbook that we're looking at. Diagonalizability is a property of a linear operator that's nice in the sense that it allows us to find matrices that are really simple. Okay, and I think the best way to understand this is just to dive in and look at the definition. Okay, so a linear operator T on a finite dimensional vector space is called diagonalizable if there's an ordered basis for that vector space so that the matrix relative to that basis is diagonal. Okay, and what is a diagonal matrix? Well, it's a matrix that has zeros everywhere except on the main diagonal. Okay, so it's a really simple matrix in the sense that it's got lots of zeros in it. Okay, and we'll make a similar definition for a square matrix A. We'll call that matrix diagonalizable if the linear operator LA, left multiplication by A, is diagonalizable. Okay, the first big theorem of this section is Theorem 5.1, and interestingly, it tells us there's a connection between this diagonalizability property and eigenvectors, which is what we studied in the last section. Okay, so let's fill this in together. Okay, so a linear operator T is diagonalizable if and only if there exists an ordered basis beta for V consisting of eigenvectors. Okay, notice that this is an if and only if statement. So we have diagonalizability if and only if it's possible to find a basis for our entire vector space that has only eigenvectors in it. Okay, and then the second sentence of this theorem gives us a little bit more information about what that diagonal matrix is going to look like. Okay, so if we start with an ordered basis of eigenvectors and we form the matrix relative to that basis, then it turns out that the matrix of our transformation, the thing that we're calling D, is going to be a diagonal matrix that has eigenvalues along the main diagonal. That's basically what this statement here is telling us. Okay, now proving this theorem in its full detail would take quite a long time, and so what I'd like to do is to just give a sketch of the proof in one direction. Okay, so I want to emphasize that this is not a formal proof. We're gonna skip some of the details here. Okay, just give you an idea of why one direction is true. And we're going to look at the reverse direction. Okay, if you're interested in the forward direction, you're welcome to look in my written notes. Okay, so the reverse direction of this theorem would be looking just kind of at the first sentence here. Well, let's just look at the first sentence here. Okay, what would the reverse direction be? Okay, well, the theorem says if our operator is diagonalizable, then there exists an ordered basis consisting of eigenvectors. Okay, we're going to do the reverse direction, so we'll assume that we have a basis consisting of eigenvectors. Okay, so a basis beta. Let's give those eigenvectors a name, v1 through vn. Okay, and what we're going to do is to build the matrix of T relative to this basis. Okay, remember what we're trying to show here. We're trying to show that T is diagonalizable. What we're hoping is that by building this matrix, we're going to wind up with a diagonal matrix. That will demonstrate that T really is diagonalizable. Okay, so how do we build a matrix for a linear transformation? Well, we start by substituting in the vectors in our basis, one by one. Okay, and what's special about these vectors? Okay, well, if you look back at our assumption, we made the assumption that all of those vectors are eigenvectors. Okay, and the definition of an eigenvector was when you substitute it into your linear transformation, what comes out is a constant multiple of what you substituted in. Okay, that number lambda 1 is just the eigenvalue that goes with v1. Okay, and that's true for all of these. Every input, since it's an eigenvector, is a scalar multiple of that input. Okay, and now we're building a matrix, so we're asking the question, how would we write those outputs as a linear combination of the same vectors that we started with? So it's like filling in the blanks. Okay, and can you help me out here? So how do we write lambda 1 v1 as a linear combination of v1 through vn? Well, all we really need is a lambda 1 there and zeros everywhere else. Okay? And similarly, if we move down to t of v2, same question, how would we write that? Excuse me, let me fix that. Okay, and there again, because we're trying to write lambda 2 v2 as a combination, it's not too difficult to see what we need in the blanks, just a lambda 2 in front of the v2 and zeros everywhere else. Okay, and then finally we work our way down to lambda n vn. That's going to be zeros in front of everything. Okay, except lambda n in front of vn. Okay, and what I'd call your attention to is all of the zeros that we get here. Okay, so really the only place that we don't have zeros are the places that I'm circling. So what would our matrix look like relative to this transformation? Okay, well, let's see. So the first column of the matrix is going to be obtained by looking at the coefficients in front of our VI's up here on this line. Notice that we're just going to get a lambda 1 in the upper left-hand corner and zeros everywhere else. Okay, what about the second column? Okay, well there, bunch of zeros again, but a lambda 2 in the second position. And you can kind of see what's going to happen here. We're going to get zeros everywhere except along the main diagonal. And what we end up with here is a diagonal matrix. Okay, there's our demonstration that T is diagonalizable. We showed that this basis of eigenvectors produces a matrix that's diagonal. Okay, and another thing, well, let's mention that first. Okay, another thing you might notice is what are the numbers that are along the main diagonal? Well, they're exactly the eigenvalues. If you look back at the statement of the theorem, that was what the second sentence in the theorem said, that this diagonal matrix is going to have the eigenvalues along the main diagonal. Okay, that completes our sketch of this argument. I want to mention, though, one point of notation here. The way that I wrote out my matrix, it's okay to write it that way, but I want you to be aware that very often this is abbreviated. Okay, so we wrote all of these zeros. A lot of times when you have a matrix with a bunch of zeros, you don't write the zeros, and it's kind of understood that those entries are just zero that you didn't write. So in other words, we could have written this matrix like this. Okay, and it's understood to mean where all of those blank spaces are, there are just zero entries.